Hello, ladies and gentlemen, and welcome to our OI Analytical webinar. This is the first part of a two-part series on our automated chemistry analyzers, featuring our special presenter, Hank Hahn. Before we continue, before I introduce him, I'd just like to remind you all that everyone is muted. However, we do have a FAQ, a question and answer session at the end of the presentation, which is open to everyone. You simply type your question into the chat box, which is on the interface, the right side of your interface. Without further ado, Hank, thank you very much for joining us.
Thank you, Michael, and thank you everybody for joining today as well. Going to have an introduction to automated chemistry analyzers and also talk about our FS 3700. As he mentioned, it's going to be a two-part series. So today we're going to start off with the introduction to the FS 37 automated chemistry analyzer. So what we'll cover is why the need for testing, why the need for automated chemistry analyzers, what is an automated chemistry analyzer, and then also history of ACA, Alpkem, and OI Analytical. First, I want to talk a little bit about Xylem. So who is Xylem? We're one of the world's largest leading water technology companies. Revenues of $5.25 billion in 2017, have over 16,500 employees. We're in 150 countries and cover 7 continents. We bring together some of the most progressive brands from transport to water treatment to dewatering, applied water solutions, and then measurement control solutions, and we're within the analytics group here. Our analytics breakdown is the process team does about 30% of revenues, laboratory 25%, ocean 10%, and surface waters cover 35%. Wanted to give a quick history of OI Analytical. We were founded in 1963, so we have over 5 decades of experience. We were a U.S. publicly traded company and was purchased in 2010 by ITT. We were known as Oceanography International, and our claim to fame was some of our original instruments were total organic carbon analyzers. We worked in conjunction with Texas A&M University here in College Station, Texas, and did a heated persulfate TOC analyzer. ITT split into 3 major groups in October 2011, with the principal water business becoming Xylem, and that is the umbrella we're in. We've had some integration of different products with Royce, GWI, US distribution of some different products and such. So we've had a long history of providing analytical instrumentation. We do offer a world of solutions, so we do have some other platforms. We do total organic carbon analyzers. We also have a GC product line with sample introduction products that can interface to GC and GCMS instruments. We'll be covering automated chemistry analyzers. We also have selective detectors, and we can interface to gas chromatography systems as well. So presenter, I'm Hank Hahn. I'm currently OI Analytical Senior Sales Specialist. I'm based in College Station, Texas. Have nearly 30 years of analytical instrumentation experience, including the product lines we have with gas chromatography, automated flow chemistry, and TOC analyzers. Sales colleagues refer to me as a valued resource. I provide a lot of knowledge and not only my understanding of the technical side of our instrumentation, but also have an understanding how it best provides solutions for various applications in the numerous industries we cover. So we'll start with why the need for automated chemistry analyzers. So why do environmental laboratories, municipal or industrial facilities do environmental testing? Commercial laboratories analyze samples for a profit. Municipal laboratories analyze for process control and to satisfy a permit. And industrial facilities test to meet permits. Environmental testing labs run methods, not instruments. Methods are a prescription. The method defines the method detection limits, calibration range, QC acceptance criteria, extraction, preparation, and the instrument. Most importantly, our customers are looking to buy an instrument with the ability to run a method. So why test? So I'm going to cover some regulations here that we have in the United States. US EPA drives a lot of that with the Safe Drinking Water Act and Clean Water Act. There's also the Title 40 Protection of Environment Part 136 guidelines. establishing test procedures for analysis of pollutants. There's also an NPDES permit program that addresses water pollution by regulating point sources that discharge pollutants to waters in the United States. There's also ASTM committee that studies water. That D19 committee covers the automated chemistry analysis of ammonias and cyanides, and also total organic carbon falls under this committee as well. There's also a standards methods, the SM 4000 series, and that's for the examination of water and wastewater. Why do people test? Here in the United States, we have like a Safe Drinking Water Act, and so what you get in your bill is, say like with the City of College Station here, get the facts about your drinking water. Here you have to do measure for total organic carbon. Also, there's a need for measure of nitrate, nitrites, and such as well. And why do people monitor for nitrate, nitrites? Nitrate is a water-soluble molecule made of nitrogen and oxygen, formed when nitrogen from ammonia or other source combines with oxygenated water. It's naturally found in plants and many foods, tasteless, odorless, and since it does not evaporate or bind well to soil, it's used by plants and stays in the water. Nitrate reacts with oxygen depletion in water, which causes fish kills. So sources of nitrates are fertilizers, animal waste, human sewage, decaying plant debris, and industrial waste as well. Some of the concerns are baby blue syndrome as nitrate changes to nitrite. Pregnant women should not drink if contaminated with nitrite. People with heart or lung disease, inherited enzyme defects, or cancer more sensitive, also causes brown blood disease in fish. So in the markets, there's the ACA market with customers. So some of the big applications are cyanide. You'll find those environmental labs, industrial plating, gold milling, commercial laboratories. There's publicly owned treatment plants that'll be doing treatment, drinking water, industrial labs, and gold mills. Phosphorus, your total phosphorus, and also your orthophosphate. Big in environmental, again, commercial laboratories, publicly owned treatment works, universities, agricultural, federal, state, county, and local and industrial labs. Nitrogen, which has the nitrate, nitrite, ammonia, and TKN that falls under that as well. That's the environmental market. Commercial, again, publicly owned treatment works, universities, agricultural, federal, state, city, local and industrial laboratories doing testing, and also phenol, environmental market, and again, those same industries. With the industry market segments using ACA, there's drinking water facilities, and what they're doing is they're looking for free cyanide. We have a method, OI 1677, and then also too, there is cyanide by post-distillation with an ISO method. There's nitrate, nitrate, nitrogen, your nitrite, nitrogen, without the cadmium reduction, and then your orthophosphates. We have wastewater facilities that'll be doing treatment as well. They're publicly owned treatment works in the United States. They treat the wastewater, remove the harmful pollutants, making water safe for the environment. There's your non-publicly owned treatment works. Those would be your refineries, chemical plants, metal plating, power plants. There's over 95,000 facilities in the United States, and these facilities are issued those NPDES permits as they discharge into the navigable streams. They've got to monitor that water in the plant and water discharge from the plant. So basically, they've got to put the water back as they found it if they're using it. Some of the chemistries and such that is of high importance with these permits, there's ammonia, nitrogen. We follow a lot of the EPA methods and protocols, nitrate, nitrogen. There's your orthophosphate, your total phosphorus, TKN, total phenolics, and then also folks are looking at total cyanide. Industry segments with the NPDES, the Clean Water Act prohibits anybody from discharging pollutants through a point source into water of the United States unless they have an NPDES permit. The permit will contain limits on what you can discharge, monitoring and reporting requirements, and other provisions to ensure that the discharge does not hurt water quality or people's health. So we have a really nice example of a client here in the Houston Ship Channel area that has a permit. They were farming their samples out to a local water authority, so they had to await the results, which could take several hours to get those results back and such. So they were kind of holding on to water and such and not being able to release that. So what we did is we did a demonstration there doing our total cyanide, and also we have another cyanide method that is for the available cyanide. So we performed a demonstration there, showed proficiency, and they purchased the system. And then by allowing them to purchase this system, they can test immediately, get the results they need, can see, oh, if we need to retreat the water, or we can release that per our permit. There also are environmental and contract laboratories, and they're basically following sort of along those same methods: your ammonia nitrogen, your nitrate nitrogen, your orthophosphate, your total phosphorus again, TKN, your total phenolics. Now also it brings in available cyanide and the total cyanide as well. We do have ISO methods as well. So that is the International Standardization Organization, Worldwide Federation of National Standards Bodies. Work of preparing international standards is normally carried out through ISO technical committees. So some of the methods that we have is a free cyanide, ISO method 14403. The total cyanide also falls under that method. That's a post-distillation cyanide methods. We also have NBAS, ionic surfactants, and then also we came up with a application too from the ISO method 14673 for NO2, NO3 in milk. So the big thing again is environmental testing. Nitrogen and phosphorus make up a lot of the testing. It accounts for over 80% of the analytes measured by automated chemistry analyzer. Well over half of these analyses are for the simple nutrients ammonia, nitrate, nitrite, and phosphate. The remainder is total nitrogen and phosphorus either by Kjeldahl or persulfate digestions. There's also precious metal extraction, plating, petro and chemical analyses. Gold's extracted from ores using cyanide solution. Our gas diffusion ampermetry methods for free, available, and total cyanide were developed because these are the only methods known capable of accurate determination of cyanide in these other matrices. We offer a laboratory and also an online device as well that we've installed in gold mines across the world. Also, we have some tobacco applications as well, methods developed for quality control testing of tobacco products. So why automation? The purpose of these analyzers is to automate wet chemical analysis to exactly reproduce reagent addition, reaction, timing, mixing, and measurement time. Currently, these labs may be using ISE, ion selective electrodes, spectrophotometer, titration, and these are all manual interaction. There are several types of automation that's available. There's segmented flow analyzers with segmented flow. There's flow injection analyzers with FIA. Also, there's discrete analyzers on the market. So automation saves time, decrease cost, improve quality, and reduce waste. Automation is having a machine do things for you, releasing you from repetitive tasks and allowing your laboratory to analyze more samples per day, and at the same time improve long-term method performance. Anyone looking to increase throughput, increase overall laboratory capacity, should consider some form of automation. Extra benefits include waste minimization and decreased cost. If you're looking to increase your lab's efficiency, then should consider automation. One thing with automated chemistry analyzers, it is microflow, so you're using low amounts of reagents using the instrumentation. Also, with waste minimization, there are potentially some hazardous chemicals that you're using with the distillations and such. You can remove those hazardous materials from the laboratory, and also that cuts down on cost of waste disposal as well. Benefits of automating: do more samples, gone or pipetting, reading colorimeters, ion selective electrodes. More samples per day means more profit if you're talking or working with an environmental laboratory. Environmental labs exist to make a profit. Water treatment facilities and lab and industrial facilities, while they might not charge for tests, still a profit by letting the instrument do the work for them. Automated instrument lets you gather more information and keeps working multiple shifts and overnight. It's feasible to accomplish 3 times the work you can do manually in an 8-hour day. Almost any method can be done manually that can then be automated. Regardless of the automation technique, they all do about the same thing, and that makes the lab's analyst's life easier. Manual methods can possibly be nature and error prone. Analysts get tired, or because pipetting, mixing, or so forth just varies between analysts. Manual methods limit a laboratory's ability to do more samples per day. Analysts will stand at the machine to record every measurement. Automation equates to better results and also lower cost per test. Laboratory costs can be reduced by automation. Some of the higher laboratory cost is the direct labor, indirect labor, and then operational supplies. So at most labs, the most expensive cost is the labor and then the supplies. So another spin on automating wet chemistry analysis is flow analysis has advantages over manual methods that include smaller sample volume and reagent consumption, greater reproducibility, higher throughput. Typical continuous flow methods can analyze samples from 30 to over 100 samples per hour. Normally, throughput is limited to 30 to 90 samples per hour to allow baseline resolution between samples, better detection limits, and a larger calibrated range. Since continuous flow methods, segmented flow and flow injection, analyze every sample and standard at exactly the same time, following injection into the continuously flowing stream. Reactions do not need to be brought to equilibrium. Some terminology that you might see with automated chemistry: continuous flow analysis, CFA, the analysis technique in which the sample becomes part of a flowing stream where operations take place. Sample is carried from the injection point to a flow-through measuring device and then to waste. What techniques you'll most commonly see again is segmented flow and flow injection. You have your analyte, specific substance being identified or measured in analysis, accuracy, baseline, the steady transmission level appearing on detector display when liquid flows to the flow cell, calibration curve, graphical representation obtained when a concentration versus voltage or peak height output curve is prepared by a number of standards or calibrants, carryover, sample-to-sample interaction, a detector that measures the absorbent fluctuations of the analytical stream resulting from color development as the reagent and analyte react. On the photometric detector, which we use within our system, the output is a digital response proportional to the absorbance. A flow cell is the optical cell that allows the light absorbance to be measured on a continuously flowing liquid stream. Have flow rate, heater. Some of our analysis utilizes a heater, heats a sample from 37 degrees Celsius to 50 degrees Celsius. Injection valve that's used with flow injection. It's an 8-port valve, regulates the volume of samples introduced into the FS 3700 system. Interference filter used in the photometric detector that separates the light wavelength that enters the detector before the light passes through the analytical stream. Linearity, degree of proportionality between the peak height and analyte concentration. Mixing coils, we have a series of loops or turns on a cartridge that create the mixing action, allows the time delay needed for the chemical reaction. You have your method detection limit, your minimum level of detection. We also have a precision pump that pumps a system moving the liquids by compressing flexible tubing between a solid surface, platen, and a roller. Precision, that's the degree of mutual agreement among data that have been collected in the same manner. Pump tubes, which we use in each chemistry, they're calibrated plastic tubes installed on the pump patents, stretch across the pump rollers. They deliver samples, reagents, and the air to the analytical cartridge. Flow rate of the pump tubes depends on the tube's internal diameter and pump speed. They're color coded on each tube and identify the internal diameter of the pump tubes. We also have the relative standard deviation, the RSD. This is a statistical measure of the precision which the deviation of multiple measurements are expressed relative to the average value of the measurements. Reagent blank. Reagent, that's the chemical substance or material that aids or creates a specific chemical reaction. Reagent blank, an aliquot of reagent water or blank matrix is treated like a sample. Have your relative standard deviation, the RSDs, statistical measure of precision, in which the deviation of multiple measurements are expressed relative to average value of the measurements. Sensitivity, the ability of the method to discriminate between sample differences in analyte concentration. So what is the automated chemistry analyzer and the techniques? An automated chemistry analyzer, the purpose of these analyzers is to automate wet chemical analysis. And again, to exactly reproduce reagent addition, reaction, time, mixing, and measurement time. And again, there are several types available. So a continuous flow analyzer consists of a pump that moves reagents through a manifold composed of tubing with T's for the addition of reagents, sample and coils for mixing sample plus reagent, and creating time delays that allow reactions to proceed. How the sample volume is measured and injected into the tubing is a primary differentiator between segmented flow and flow injection, the two major divisions in continuous flow analysis. Segmented flow uses air segmentation to separate sample segments, allowing for better mixing and decreasing carryover between sample segments. And FIA does not segment with air and relies on dispersion that occurs within the tubing mix, the sample. Since there's no air segmentation, FIA chemistries proceed rapidly through the cartridge. So what you see here is an example of segmented flow. You have your sample and there are the air bubbles between each of the sample aliquots. So again, the principles are flow, mix, react, and detect. So with the OI flow solution, we apply continuous flow. Continuous flow refers to samples aspirated, reagents added, color produced, reaction occurs, concentrations are measured, and results are processed, all in a continuous flow. And our flow solution analyzer uses both segmented and flow injection techniques. Cyanide, again, which is a really popular chemistry, is the CN solution involves injection of sample into a carrier stream. Once injected, the sample is segmented and acidified to release hydrogen cyanide, which passes through a hydrophobic membrane. HCN is absorbed in acceptor solution and directed through a flow cell where the cyanide is measured ampermetrically at a silver working electrode. So an example of segmented flow analysis, have a little diagram here showing from your sampler to your pump to the channel cartridge to detector to the software. The sample is aspirated from a sample cup. It's pumped into the analytical plate where segmentation and mixing with reagents occur. Air bubbles are injected as sample progresses through the system. It can be heated to create desired chemical reaction. Since the process might be long, air segmentation serves to minimize sample zone dispersion carryover. Chemical reactions results in a chemical which is pumped through the flow cell in the detector and measured with a nanometer filter and processed into software. So what we offer is a sampler. We have a 180 position, 360 position auto sampler, a 24 channel pump. We have chemistries, also the chemistry plate. We have the ampermetric detector, which is for cyanides only, photometric for the colorimetric methods, and then we have the flow view software. With flow injection, you add a FIA valve in the mix. So after the pump, there's a flow injection valve that is placed in front of the channel cartridge. So in that, the flow injection analysis, a precise amount of sample is injected into a continuously flowing stream by an injection valve. Reagents are added. It may be heated for, again, the desired chemical reaction. A reaction occurs and color is measured same as the segmented process. There are some analytical techniques that we'll discuss. We'll go a little further in depth with segmented flow, flow injection, and then also injection segmented flow analysis, ISFA. With segmented flow analysis, the segmented flow analysis is the first autochemistry that was invented. Segmented flow has enjoyed over 50 years of success as a proven technology. Segmented flow is the basis of multiple automated EPA and other regulatory methods. So basically, again, as we've shown, you have your sample, then you have a little gas, then sample, then gas. So the diagram here, we show samples are pumped into the continuously flowing stream of reagents that is segmented by air or other inert medium. The segmentation limits dispersion, allowing the reactions to proceed to equilibrium or maximum color development. First automated chemistry analyzers, again, used segmented flow. And again, most of the EPA methods were written around segmented flow. Since they are about the same, the EPA then approved the flow injection analysis. All segmented flow analyzers separate sample slugs from each by the air bubbles. Bubbles limit transfer of one sample segment to the next. Samples travel down the path of the tubing. The segments allow sample solutions to travel slower through the tubing, giving extra time to completely react with reagents. As the segmented flow sample travels through the mixing coils, end over end action that happens inside the coils ensure 100% mixing of sample with reagent. 100% mixing also guarantees a maximum number of collisions between analyte and reagent. The analyte reacts with the reagent by colliding with it. The idea is to make sure that all possible reactions occur, producing maximum color product for measurement by the detector. So prior to entering the flow cell, the segmented gas is removed from the stream using a debubbler. The non-segmented stream then flows into a flow cell designed for colorimetric detection. An interference filter and appropriate wavelength is required. So here's an example of a segmented flow peak. This is ammonia TKN. SFA peaks have a slight flat top, which represents approximately 95% of reaction completion to provide the highest sensitivity. Segmented flow increases throughput because less wash is required between sample segments. A flat top on the peak guarantees that all reagent and analyte have reached maximum reaction. So some of the benefits of segmented flow include low method detection limits, has excellent precision, steady state dispersion, and steady state reactions and limited dispersion. Flow injection analysis uses dispersion by injecting a sample into an unsegmented carrier stream, adding one or more reagents, mixing, heating, reacting, and detecting using continuous flow. FIA can be used for high sample throughput of chemistries and uses shorter reaction times, as the chemistry does not need to be brought to completion due to the highly reproducible injected sample volumes and the reaction times. Here's an example of a FIA peak. Since the reaction is not brought to completion, FIA peaks do not have flat tops and are nearly Gaussian in shape. Some of the flow injection analysis benefits include rapid analysis, no need for debubblers, excellent precision, higher throughput, and we also kind of recommend it to those new to automated chemistry analyzers due to the fact that it is basically a continuous flow. There's no segmentation, It's a little bit easier to operate. We have ISFA, which is injection segmented flow analysis, and that's used with nitrate, nitrite, and with total cyanide chemistries. The injection segmented flow excuse me, uses FIA to inject a highly reproducible sample volume, then segments the carrier stream with air bubbles followed by reagent addition, heating, mixing, and detection. ISFA uses FIA to inject a highly reproducible sample volume, then segments the carrier stream with air bubbles followed by reagent addition, heating, mixing, and detection. ISFA is used for chemistries requiring turbulent mixing, such as nitrate, where the sample and the ammonium chloride buffer carrier stream must be rapidly reacted with in the walls of the open tubular cadmium reactor. This is to reduce nitrate to nitrite, and it's also used within the UV lamp for the total cyanide method. So here's like an example of a cadmium nitrate cadmium coil. So the turbulent mixing generated by segmented flow actively moves the nitrate ions at the center of the sample zone out to the walls of the copperized cadmium coil to enable rapid and efficient reduction to nitrite. And here's an example of a injection segmented flow analysis peak. ISFA peaks look like FIA peaks since the sample is injected and the reaction is not brought to completion. SFA and FIA techniques on the same instrument. So OI Analytical flow analyzers are capable of both segmented flow and flow injection on the same instrument. This offers user flexibility, modular design, and increase the capability. So we'll continue with history of automated chemistry analysis, Alpkem and OI Analytical. The auto analyzer is an automated analyzer using a flow technique called continuous flow analysis, the CFA. It was first made by Technicon Corporation. The instrument was invented in 1957 by Leonard Skeggs and commercialized by Jack Whitehead's Technicon Corporation. The first applications were for clinical analysis, but the methods for industrial analysis soon followed. The design is based on separating a continuously flowing stream with air bubbles. Flow injection analysis, FIA, was introduced in 1975 by Ruzicka and Hansen. The first generation of FIA technology, termed flow injection FI, was inspired by the autoanalyzer technique invented by Skeggs in early 1950s. While Skeggs autoanalyzer uses air segmentation to separate a flowing stream into numerous discrete segments to establish a long train of individual samples moving through a flow cell. FIA systems separate each sample from subsequent sample with a carrier reagent. Hudson and Ruzicka took their idea to company Bifolk, Decatur, a Perstorp company, and Decatur became the first company to commercialize flow injection. Today, OI and Formula Latchet are the primary providers of flow injection analysis. Micro continuous flow analysis, the RFA 300, was first introduced in 1984, and that was the first micro segmented CFA system, and that was introduced to the industrial laboratory by Alpkem. Then simultaneous FIA and segmented flow instruments in the early 1990s continued development, introduced the first instrument that allowed both FIA and segmented to be run simultaneously. This instrument was the Flow Solution 3590. In 1992, Alpkem introduced the Flow Solution FS3, then followed with the FS3000 in 1996 and Flow Solution in 1997, the Flow Solution 4. In 1996, OI purchased Alpkem, a subsidiary of Perstorp, providing continuous flow capability. Decatur, the analytical arm of Perstorp, was a pioneer of flow injection in Europe since the early 1970s, and Alpkem introduced the first third generation segmented flow analyzer, SFA, as early as 1983. The combination made OI Analytical the only continuous flow analyzer company that provides both segmented flow and flow injection analysis. So some of the instruments through our history, we introduced the FS 3000 in 1995. Compact, easy to use, advanced and automated ion analysis. It combined flow injection and segmented flow on the same platform. We also had a FS 3202, which was our original cyanide analyzer that was using the gas diffusion membrane for that, and that helped eliminate the need for caustic acids, the distillation step, then also the hazardous waste that you'd have to get rid of. Then we came out with the CN solution, which was introduced in 1995, and that again kind of came off from the platform of the 3202. The 3202 was used mostly also in the metal mining industry. We were able to offer results in 90 seconds and no distillation. So in 1999, the EPA approved OIA 1677, which removed the distillation step with gas diffusion. We had the Flow Solution 4, which we introduced in 1997. It used advanced ER detection, single calibrations covering three to four orders of magnitude. With our photometric detectors, we do have the wide range, allowing for you to not have to use dilution due to the fact that the expanded range allows for wider detection. It was productive with high throughput. It was flexible with the choice of either the via or segmented, both simultaneously. It was expandable to 6 channels and also introduced our WinFlow software with that device. And in 2005, we came out with our CN 3100. That was the single or dual channel capability, and that was dedicated to available cyanide and total cyanide analysis. Utilization of UV digestion for total cyanide was used to break down all the strongly bonded cyanide. We also had another method, D6888, which allows for sulfide abatement, as some of your free cyanides will potentially have sulfide in that. So we added an acid to help break that down to 50 milligrams per liter. Then in 2012, the EPA did approve finally for ASTM method D7511, which finally removed the distillation step from total cyanides. Then in 2006, we introduced our FS 3100 and VersaChem cartridges that were snap-on and snap-off chemistries. You could do 2 channels of via and 3 channels of segmented flow. One of the nice things too, in 2012, the EPA approved gas diffusion with ammonia TKN, and that removed the distillation step. We also introduced XYZ auto samplers with the CTAC product. And in our presentation for next week, we'll go through these different chemistries that I've just mentioned, the ammonia TKN, the total cyanide, our nitrate nitrites, and also cover some of the tobacco chemistries and the ISO chemistries that we have developed as well. So would like to thank you for joining us today. For more information, you can contact me. Email address is hank.hahn@xyleminc.com, or also info@apac@xyleminc.com. I did want to mention that we do have part 2 of the automated chemistry analyzers for May 1st at the same time. Then also would like to also announce that we'll also have a TOC analysis given by my colleague, Dr. John Welsh, on April 30th at the same time. And he'll go over our laboratory TOC analyzers, which include combustion TOC and heated persulfate TOC analysis. So I'd like to thank you again for joining us today as we had this introduction to automated chemistry analysis.
Hank, thank you so much for your time today. We really appreciate it. A very informative webinar. We actually received quite a few questions already, very interesting questions. One of the main questions was actually, will you be offering this recording? And can we get our hands on a copy of the presentation? So I'd just like to assure everyone that approximately 30 to 60 minutes following this presentation, a link to the recording will be made available and will be automatically sent to you via an email from GoToWebinar. Anyone who is interested in getting their hands on a copy of Hank's presentation, you can contact either Hank himself directly or info.apac, which is on the screen at the moment, and marketing will support you with a copy of the presentation. So at this point, I'd like to open up the webinar to questions and answers. Again, feel free to type your questions into the chat box and we will go through them one by one. If we run out of time, Hank will have a copy of all questions and he can contact you and follow up on these questions with you directly offline. So Hank, first question, concerning the software, is this compatible with Mac?
No, excuse me. Unfortunately, it's not. Our software is Windows based. It is Windows 10 uh, capable. Will operate on Windows 7 and 8, and since Microsoft kind of stopped the support of those, we kind of recommend Windows 10 Pro. Our software, which we'll cover next week as well, is also 32 or 64-bit.
Great, thanks. And the next question, there's quite a few flowing in at the moment. That's fantastic. Great response from our audience. Um, is filtration required prior to analysis to avoid any blockage?
Um, with certain samples, would say yes, since this is microflow technology and pump tubes and coils, we do recommend filtration. And again, also, it's sort of dependent on the actual chemistry as well. Uh, we have done some applications, say for instance, with soil plant, with KCl extracts and such, and digestions. That has not. It basically would, I guess, depend upon the application and the analyte of interest. And we could always help answer that too with the specific chemistry that you might be interested in.
Terrific. Next question, can this analyzer be used for effluent water? And if so, could you possibly share an example of an application?
Oh yes, with effluent water, ammonia TKN in wastewater is one of the largest chemistries requested here in the United States and in other applications around the world. That is a wastewater application, and have a white paper on that, and I'll have that information next week. Total cyanide as well is another really big one, chemistry as well in the wastewater. Your phosphates in the wastewater, and also we do cover drinking water methods, but a lot of these are written with the wastewater in mind. All of our cyanide applications, be it the ampimetric with gas diffusion, or the ISO methods with the post-distillation photometric detector, all are cover the wastewater spectrum.
Good. This is a great segue to the next question concerning cyanides. Is there a limit detection for cyanides?
Yes, in one of my earlier slides, I had the detection limits. I apologize, I can't recite them right off the top of my head. but per the method. And next week, what we'll do as well as I'll have examples of those. We also do have method abstracts that we can provide as well that will break down the method detection limit, sample throughput. They kind of have a little bit of a synopsis as well of what occurs with that. And so we can supply those to you as well, to anybody who'd like to have a copy, and that'll break that again down. And again, I apologize, I can't recite them right off the top of my head.
All right, next question. Will there be any additional hardware improvement developments? For example, auto dilution of control standards, etc.
Yes, we are looking to incorporate distillation, excuse me, auto diluter into our instrument. That is one of the big requests. A lot of people like to do that to do the making their standards, auto calibration such. So yes, we are actively pursuing and looking into uh, adding that to our product line.
Terrific. The next question is actually quite popular. It's been asked a number of times. Is this analyzer suitable for solid sample analysis?
No, it is it is a liquid based instrument. Does not do solids. You would, in the cases of say like that, you would have, like say for TKN or total phosphorus stuff, you'd have to do the digestion step and break down those samples. So it's a kind of a fluid based instrument.
Fair enough. Next question. Um, can we expect to have more methods such as total nitrogen, total phosphorus?
Yes, we have in the process of working on total phosphorus and total nitrogen using the same UV digester that we do with the total cyanide. Those are being developed and completed, and look to have those out later this year as well.
Terrific. And of course, as those come out, we will promote those and send out an email to notify everyone. Next question is concerning the minimum sample that the analyzer can handle. Is there a limit?
That is a good question. I was trying to scan through some stuff since it is microflow, and we can get that answer. I would say one example is that there was this company here in the United States that was very interested in using our product due to the microflow injection, and we could get that answer and such if have that. And one of the reasons why they liked that is because they had a serum, and in the process there was cyanide being broken down, and they needed to make sure that happened. And so that serum was very expensive to draw out. So they liked the microflow technology of our product, and due to the fact that they didn't have to use a large sample size. I don't have it readily available right here on the minimum injection amount, but we if you like, we can try to get that answered for you.
Okay, great. Thanks, Hank. Next question. I think you've already addressed this, but perhaps just to expand a little further, is there an inline filter option? And if not, what is the maximum particulate size that the analyzer can accommodate?
There is not an inline filter, um, and it would depend upon the chemistry and the pump tubes. Each chemistry has a different pump tube diameter, and then also with the mixing coils. So per the method, and then potentially on the abstract, we could have that information. Again, also it's dependent upon the application as well. But the answer to the question is no, we don't like have a built-in inline filter.
Okay, thanks, Hank. We're actually getting quite a few questions about the applications for this analyzer. Is this only for water treatment?
No, it can be used for drinking water applications as well. One really unique application is we have a low-level orthophosphate chemistry, and one community here in the United States that has to do 100% recycling of their water, since they're out in the desert, utilizes our low-level orthophosphate method as they're looking at the treated water so that it can then release that for consumption. So it is also available for drinking water methods, just not wastewater or effluent.
Yeah, again, for our audience, if you are still curious about the various applications for this analyzer, please don't hesitate to reach out to Hank via his email that's written on the screen. I'm sure he can expand on this and help you understand whether or not your proposed application is applicable or not. Next question, Hank, is what type of carrier gas can be used?
There is no carrier gas with our instrument. With nitrogen, we do provide a nitrogen pillow, and that's used for that ISFA for the segmented injection application. So like there's no gas that's hooked up to the instrument. We just have like a little nitrogen pillow, and that is pulled out via a pump tube through the pump.
Great, thanks, Hank. Another question about the analyzer's capabilities to accommodate or measure other parameters. How about sulfate, sulfite, chloride?
Yes, we do have the ability to do chlorides. That follows an ISO method. We do have sulfate as well. Uh, that follows an EPA protocol, and we are completing a sulfide chemistry as well. We had a whole bunch of chemistries on our prior product, so what we've been doing is porting them over onto the FS3700 platform, and always willing to take requests and such, and develop those chemistries and have those available. So we are completing the sulfide method and should have that available end of Q2.
Oh, excellent. Okay. It looks like our final question is here. I spoke too soon. There's more coming in. Concerning the software, can it automatically substrate the background? I'm assuming they mean background noise.
Um, I believe it can do that with the expanded range detector, and I have a slide for next week that talks a little bit about that, where with the expanded range that we have, that does sort of, I would say I wouldn't say like totally eliminate it, but it certainly lowers it. And we'll have some examples next week.
Okay, excellent. All right. Well, we're nearing the end of our webinar, and there are actually quite a few questions still remaining. So these questions will be shared with Hank offline. And Hank, I kindly ask you to follow up
Oh,
with our
certainly, yes.
attendees on these.
Hmm.
Great, terrific. So again, Hank, thank you very much for your, what time is it there in
Oh,
Texas?
it's 8:56 here in Texas.
Yeah, okay, so almost 9 p.m. Thank you so much for your time, and thank you everyone for attending this webinar. Just a reminder that Hank will be back on May 1st, same time, part two. If you haven't registered, there will be a link available in the follow-up email coming out from GoToWebinar. Feel free to register there, and we have quite a few webinars that are available to watch at your convenience in our Stay Home, Stay Safe series. Please check them out and feel free to register. And do please stay safe, and we'll see you here again next week. Thank you very much, everyone. Thank you, Hank. Have a good night.